Hello, this is Robert Gertz with the Civil Engineering 5387 class at CU Denver under Dr. Jason Radecki, and I'll be doing my presentation on classifying solar farms using satellite imagery. So as a brief overview, solar photovoltaics are quickly increasing as a percentage of total generated electricity both in the United States and the world at large. And solar PVs generate irregular electricity due to intermittent cloud coverage. So as you can imagine, whatever the designed capacity of an array is, pretty quickly drops to zero as soon as a cloud flies overhead and is blocking the rays from hitting it. And this irregularity makes efficient grid management really difficult. Especially as solar becomes a larger percentage of the grid as a whole. So in order to help with this problem, a comprehensive catalog of photovoltaic systems by location and size is really becoming necessary. And satellite remote sensing presents a really good opportunity to make this happen just from a single source, creating a comprehensive catalog. So getting into some of the methods that I used for this. The first route that I sort of went down was to try to find large solar farms within the state of Colorado. And unfortunately this proved pretty ineffective due mostly to imprecise location data. A news story would maybe say, this new system is near the town of Severance, Colorado, or is located in southwest Colorado state. And that is not good enough to really find the systems. And the second problem is that the only solar farms available within Colorado are really essentially under construction now or were completed within the last few months. And so there's either no satellite imagery available for them yet or really bad satellite imagery with lots of cloud cover. So in order to solve this problem, I broadened my scope to basically look at all of the largest solar farms within the world. And Wikipedia actually proved a really valuable resource for making this happen. So here's Wikipedia's page for the world's largest PV power stations. And you can see China recently just built the biggest one, which is just a bit bigger than the United States' biggest solar farm called Solar Star. And then you have Topaz Solar Farm, Desert Sunlight Solar Farm in the United States, and then skipping the second China system, the Copper Mountain Solar Facility in the United States, and then going down to the bottom of the list, the Agua Caliente Solar Project. So the ones I just mentioned, the biggest one and the next 5 United States systems, are the systems and locations that I conducted the following process for each of them. And the other really nice thing about the Wikipedia page is the location column you see there with geographic coordinates makes it super nice and easy to find these systems both on Google Maps as well as appropriate satellite imagery for these systems. So getting into how to find the imagery, tool selection. So Dr. Radecki advised to use shortwave infrared astroimagery for identifying photovoltaic systems. So that's where I started off. And after experimenting with each data tool available at the Astro website, the NASA Reverb tool was chosen basically just for ease of use and reliability, a lack of lag, and no errors in trying to download the data. This tool requires a quick registration through a government website, and it's searchable and relatively quick with the results and pretty intuitive to use. So data selection, the geotags from Wikipedia that I was just talking about are input to create really tight bounding boxes within the tool. And after a lot of trial and error, I found that the tightest possible bounding box over a solar system is really the best way to find the best satellite imagery for it. Aster level 1 dataset is selected, and then the granules are then manually searched and selected for integrity. Basically looking for imagery with obviously really low cloud coverage, all of the available bands that I want to use, and ideally would be well centered with other features such as water, towns, etc. For better separability. And lastly, the ideal files are downloaded and opened up in Gertz Imagine. So here is an example of a ideal bounding box that I ended up using. You can see the solar farm that I was searching for, and really just placing that bounding box right over that solar farm to get only the best remote sensing images. And here is an example of a sample data grab, and you can actually see that orange bounding box down there in the bottom right of the purple square. And so this purple square is the bounding box of the actual satellite image, whereas the solar farm is completely located within that satellite image. So within the tool previewing the satellite imagery, you see something like this. A little browse images box opens up, and you can see the image has really low cloud coverage, and the smaller 3 squares in the bottom left of this shows that all the available bands are present within the file. And so this preview mechanism is a really good way to minimize the download of useless remote sensing imagery. So after you find a good image, you find the downloadable files through this screen, and the highlighted 6 lines you see here are really just 3 links. The top one with an HDF extension includes the thermal infrared bands as well as the RGB bands. The second one with the capital T.TIF is basically a more compressed file, and the capital V.TIF is a larger, higher resolution RGB file. So after downloading generally just the HDF and larger RGB files, I would open them up in Gertz Imagine, and here's a sample of the RGB file, and you can not really identify where the solar farm here is in this image, but getting into the TIR spectral bands, you can see it really pop out there in bright orange in the middle right of the image. So immediately you can see the added usefulness of the TIR bands over just RGB. So getting into the first problem that I encountered in the project, really the reason that I went to Aster Data was to try to find the shortwave infrared bands, and unfortunately the Aster user's guide says, quote, "The SWIR sensor suffered a setback due to its anomalously high detector temperatures, and this anomaly rendered the SWIR sensor essentially unusable since April of 2008. So unfortunately, the exact data I was going for isn't actually available due to the sensor failure. The second problem is that the TIR band analysis would run into data errors, or errors when I would try to perform the data analysis. I was still able to open up the TIR bands visually, as you just saw, but the data analysis seemed to be running into missing data that wouldn't allow for creation of feature space. And trying to troubleshoot this was unsuccessful. As far as I could tell, it might be connected to those missing shortwave bands or some other issue I couldn't identify. So some available solutions for the project. The thermal infrared band analysis was still available from a purely visual inspection aspect, which ended up proving really useful. And RGB data analysis was still able to be successfully performed. And fortunately, the RGB data came with a higher resolution that sort of made up, in certain ways, for the weaker separability available. So the RGB imagery was available at, I think it was 15-meter resolution, whereas the TIR imagery is only at the 90-meter resolution level. And furthermore, given more time, I probably could have tracked down other sensors or sensor data, could have been explored to try to find something for the shortwave or for data analysis of the TIR bands. So I started off each solar farm analysis with a TIR visual inspection. So as an example, I might open up the largest solar farm in the world file, that China file, and I would open it up in the TIR image file. And what I found was a combination of bands 10, 13, and 3N produced that really nice highlighted orange color for solar photovoltaic systems. And so what that does is it allows these features that in the RGB spectrum are really difficult to separate from the solar surface. It really allows that separability of those types of spaces. So here you can see what I'm talking about. Basically, the top image here is a solar system in the RGB spectrum, and you can see it appears as this dark green color. And unfortunately, some of the surrounding hillsides there basically cover the exact same part of the spectrum within RGB. But if you open it up in the TIR and use that 10-13-3N combination, the solar system really stands out and is much, much more separable. So visually, the TIR was still really useful for this reason, even though I couldn't further explore it through a data analysis. So after I would identify the location of the solar system, I would perform an RGB data analysis. And the basic process flow was to open up the signature editor, open up the draw tools, and create a bunch of AOIs for various classes, combine multiple AOIs into classes, then create the feature space, isolate feature spaces for each class, use linked screens to search for additional solar sites from the feature space, and then perform a separability analysis, particularly the Jeffreys-Matsuda. So here's just a few screenshots of walking through that process. Using the draw tool to create the AOIs over some solar surfaces here. Here's what you get with a bunch of the same solar surfaces, then aggregating them and finding other classes, then creating the feature space. And here's pretty much what all 6 solar farms feature spaces look like. This sort of big triangular feature space with a bit of a stronger pixel band in kind of a bottom left to upper right direction. And this is an example of one of the feature spaces that included a large water section that you can see down in that bottom corner. And then lastly, or almost lastly, identifying the class location within the feature space. Here you can see where the solar surface always showed up in the bottom of the highly dense pixel band. And so lastly, performing that separability analysis, and here you can see the class 1 of the China's solar system has really good separability from all the other 6 classes. So results, as I mentioned, all 6 solar farms feature spaces were very similar, and They all consisted of the same basic features, desert, mountains, some solar surface, water, farms, and some urban space. The location of the solar surface class within each feature space was nearly identical, located in that bottom right below the main pixel band. And using linked screens then enabled the location of additional solar systems present in the image that I wasn't actually aware of, which was a really nice, unexpected result. So, as far as the unique feature space, the fact that all 6 of the solar farm satellite images were really similar in their feature space kind of implies that this is an ideal feature space for building a solar farm. So that's useful and interesting in its own right, just as far as saying if we're going to look for other solar farms, these are the types of feature spaces that the image is probably going to have. Or even if we're looking to find other areas that might be ideal for a solar farm, that could also be useful information. Then, as far as the solar class location within the feature space, this every single time showed up in the same space in that bottom right. And so this reveals, only the beginning of the potential for identifying that unique spectral nature of solar surfaces. And it's really likely that including some shortwave infrared or even thermal infrared to the data analysis would reveal a really, really much more specific spectral signature for these photovoltaic surfaces. But that said, even limiting the analysis to the RGB bands, the primary goal of the study was really still successful. And the Jeffreys-Madison separability analysis shows that even though the RGB wasn't as good with the separability, it still was very significant. So using the linked screens to find additional systems was a really nice result. So by linking the screens and exploring the solar class section of the feature space, I was able to find other solar systems that were present in 2 of the images. And in both of these cases, comparing the findings to the Google Maps revealed that the systems were really not present in the Google Maps. And so there are probably solar systems that are either under construction or just recently completed construction. And so I thought this was a really nice result, since it shows the ability to locate otherwise unknown systems using this analysis. And you could easily extend this concept to higher resolution imagery to identify smaller rooftop solar systems. And so here's what I'm talking about. The top is the TIR imagery of a big solar farm that I found through exploring the feature space. And the Google Map image below it shows that just a small section of it is present in Google Maps. So most likely the majority of that extra solar farm has been completed really, really recently. So further research directions, primarily I'd like to identify functional shortwave infrared data, or at least thermal infrared data that can be further analyzed through things like the feature space. I'd like to fine-tune the spectral signature of solar surface classifications, explore the potential functionality of unsupervised classification, especially given better data and a more specific solar spectral signature that I'd be looking for. I'd like to find some high resolution imagery and attempt some automated identification of smaller rooftop systems. And lastly, it'd be really nice to be able to even identify types of solar systems by extremely specific spectral signatures, as well as more broadly, just the system sizes and estimated generation quantities by location. So some acknowledgments and links. Thank you to Dr. Gradecki for the leads and the advice. The Aster user guide was really helpful in doing some debugging. Wikipedia was really useful for identifying some actual usable information. Aster imagery main page for finding the NASA Reverb tool and using Erdos Imagine software for the analysis, Google Maps for some comparisons, and lastly the various Colorado solar farm news stories that sort of got the whole project started. So thank you for the class, and I enjoyed working on this project.